As seniors, we have to do a senior design project.
And as soon as we saw NASA, we thought, this seems pretty interesting.
It's a hands-on project, using all of the things that you've learned in the past 4 years and just making the most of it.
I think when the students are challenged, they do a lot more work and they have a lot more fun and they can work really hard and they can see that they're producing something.
We still have to have our own. That's pretty much how we formed, was just, hey, here's something you can do for your senior design project, and it's a little bit different than your typical design projects.
As far as engineering goes, mining and aerospace don't really have a whole lot in common, so.
In the engineering field, it's never a one-person job. You have to come together and build something.
It's kind of taken me out of my comfort zone, making me learn things I wouldn't normally have to do.
What I actually did in this project is actually take off electronics. I don't really have much electronic backgrounds, so he really made me learn a lot and try to do what I can.
We're pretty far behind, got a couple more weeks to get this whole robot complete, so a lot of late nights are going to be coming up.
We've been really focusing on the whole design process.
It started kind of with what kind of qualities do we need in this robot? How fast can it move? How much can it hold?
So are we using a joystick anymore? Could we just turn the motor off and on? We started off by looking at previous competitions to get a feel for what people were doing.
We originally kind of saw the bucket chain design, and that was sort of like the favorite, it seemed like.
The bucket chain, they're a hassle, and it's a good way to lose most of the material that you excavate because they just fall off. We just felt like that was kind of just copycatting, not really being innovative like NASA's wanting us to be with the competition.
We went through a lot of different iterations, but we eventually came up with the auger.
It'll just drill and hopefully bring up dirt. It's a little wobbly, yes, but I think it's kind of probably it's just going to force itself up.
And a lot of people tried to use augers in the past and didn't really get too much success. You may need something on the frame to hold it up here. And a lot of times I'll try to point out some obvious things to them, but you know, it's their design.
So basically, this is our starting position. Once we're in the digging area, we'll stop, and then we will lower the auger. So the auger's all the way down. It's been spinning, and the dirt's been pulled up into the bucket.
That mold right there, that's going to be the outside, then we're going to put the carbon fiber on the inside. We chose carbon fiber because it's the lightest material. Originally we had aluminum, but a little too heavy, and it went over our weight restrictions.
We went through, I think, 20 different designs, something like that.
It's changed a lot. There's been, like, the design we have now has been a revision of a design that we had, and it's like the 4th revision.
We've just been throwing ideas back and forth off each other.
Stop. I did.
We're always running into problems, always having to solve the problems.
Okay, how do we steer it though?
I don't think that's gonna work.
Stop!
Something will break down and we can't figure out the problem, so we're all like down on ourselves, and then we figure out the problem and we're feeling really good again. And it's a giant roller coaster of emotions.
It took us, I think, like 4 months to finally get something nailed down that we could use.
We have all the pieces that we need, so we're kind of just trying to put everything together now.
Things could go wrong, but we feel like we planned pretty well, and we're hoping to do pretty well.
It is a challenge. The frame is made from 80/20 extruded aluminum. It's called the industrial erector set. As a mechanical engineer, I was concerned that it could hold 60 tons of dirt. Did some analysis and decided that we needed some extra joining plates, some extra structure. We wanted the students to basically understand how tough of an environment the surface of the moon is. Lunar regolith is dry, gritty, very dusty, very fine particles that get in mechanisms. We want them to solve the problems of traversing in a harsh environment, excavating really stubborn dirt that doesn't want to be excavated, and then being able to lift it and deliver it. So that was like a moment of big relief. So we're going to make our schedule. Not going to disappoint all these college teams that are on the way.
Everything's so reflective.
We didn't go to sleep at all Sunday, so it was early Sunday morning till 12 o'clock, and then we packed up and then left at 2 o'clock.
It seems like every day we wake up really early, start working on the robot, and we say, okay, today we're gonna get done early, we can go out, that sort of thing. But it's robot, robot, robot.
They stuck with it. They could have just slacked off, but I think they were really excited to come down here.
We were just so focused on building the last few parts and putting it all together that we didn't really have time to test it as much as we would have liked.
Yeah, the last couple of weeks is definitely a big push.
We knew the fundamentals worked, it's just a matter of will our program work with this, because we never actually tested it.
The objectives of the Lunabotics mining competition, in order to win, you have to excavate lunar regolith simulant, so that's simulated lunar soil, in a large box. And you have 2 competition attempts, which is 10 minutes for each attempt. And the team that scores the most points while excavating this lunar regolith simulant wins the competition. We call these robots Lunabots, and a Lunabot excavates lunar soil or Mars soil, and the reason why we excavate it is because the soil contains all kinds of minerals which are a resource, valuable things for us like oxygen or nitrogen or actually even water. We think there's water ice on the moon, but it's below the soil. To access the water, which is valuable for human existence and for propulsion, we need to dig down to 30 centimeters to get the ice.
Some of the people were already graduated, so they just like give up on the project. So I took over the Friday beforehand. So I have about a week to actually finish off the programs, and I did what I could. So.
Well, ladies and gentlemen, welcome to the first annual 2010 Lunabotics mining competition.
Well, I'm very impressed with the students and what they bring to the Lunabotics event. It actually takes me back to when we were just getting started in the Apollo program more than 40 years ago. The competition really is an important bridge to the future of space exploration, something that we definitely need.
First we found out we were too heavy.
We were about 20 pounds overweight the first time we weighed it, so we had a lot to do after that.
First, we actually changed the tires.
We were able to switch out our large foam-filled wheels with some lightweight aluminum ones.
Our custom-made wheels we haven't tested, hoping for the best, and they actually ended up working, so that was great.
And that saved us about 12 pounds.
From there, we just started hacking away at our robot, cut some of the aluminum plates off, started cutting holes and stuff.
Shaving off bolts and doing whatever we could.
And we take some of the side panels off. That actually exposed our electronics, but that saved us another 3 or 4 pounds.
Hold the pallet. All right, let's square it on it.
79.3. Well done, gentlemen. Well done.
And we ended up being about 0.7 kilograms underweight, so we cut it pretty close, but we made it. The first practice session, we basically wanted to just test out some movement and just sort of the auger's drilling capabilities.
Keep trying to turn if you can. This is the max turn.
We were having trouble with our maneuverability of our robot. Went into the excavation area, excavated a bunch of stuff. Engine started smoking. few of the wires end up like falling off.
I mean, I was actually kind of pleased with it because we actually had never really seen it excavate and actually material come up in the bucket. So we saw that and I was like, well, it wasn't too much, but it shows the design works and we were kind of still worried about that. Second test, we were just trying to test our mobility and just being able to turn and drive.
And we started the robot facing away from the digging area to practice the turning. And basically we found out that the way that we had been trying to turn, which was basically one set of wheels moving forward, the other one moving backward, didn't really work at all because it kind of just locked both motors up.
Our wheels are completely limited to going straight forward and straight backward.
So we ended up drilling down. We actually weren't able to get anything there either. It kind of just stopped working. The auger came out of gear and there wasn't much we could get done.
That practice run, we didn't really get a whole lot done, definitely not as much as we intended to.
We went backwards a little bit, but we did figure out how important turning was.
It's really frustrating to learn a new programming language in a week and apply it to control a robot. And that is actually a really hard thing to do. So, I don't know.
This was all kind of dumped on him, so he's in his own kind of panic, frustrated state, and time's ticking, so we're all just running around trying to find fixes.
We were down to 3 hours beforehand, so there were a lot of pressures building up and things just starting to fall apart, I guess.
None of these guys really had much electrical experience, and that was a key component for this competition.
We had about 3 hours left before they were going to quarantine the robots, and we knew that we needed to get the movement system down, and that was our big, challenge that we still had left.
Everybody was starting to get agitated by each other. We figured it wouldn't be that hard to make a turn, and apparently it was. And we were doing everything we can, changing the programming each time, trying to figure out exactly what we needed to do, and it still didn't work.
We ended up just having variable speeds on each side, like the left side would go slower, the right side faster to make a left turn. And that actually ended up working pretty well.
We're always looking for new solutions, better solutions. And so we'd like to take the out-of-the-box thinking from somebody that comes in from the outside, like these students, fresh minds, fresh thinking, and we'd like to see what they come up with. If they have some good ideas, then we would certainly like to talk to them about their ideas and possibly even incorporate those into our designs.
See what we got here. For Team A, Virginia Tech.
Oh, well.
It was pretty stressful. I'd say we were a little nervous.
We needed to hurry and get set up real quick because we got here a little late this morning.
In our practice runs, we weren't really able to do everything that we wanted to do. We thought, we still might have a decent chance of being able to move around, but it was really kind of a, we'll just see what happens type thing.
You kind of learn that a lot of things can happen, really unexpected, and you just have to pick it up and just do the best that you can.
We were hoping it would turn, but we realized that one side wasn't operating at all, so we were kind of sitting ducks.
We were trapped in the starting area.
So we kind of were like, well, we can't move, we might as well show our design works because, that's kind of the point of this competition is the excavation method. The maneuverability and other things, they're important, but the excavation is the purpose of this competition. So we're like, we'll just show our design works, and we started digging.
It seemed like it was pulling up the dirt even better than we kind of expected it to.
You gotta go into it.
good auger first.
We went as deep as we could, and apparently flames started coming out of our motor up top, and we cut the power and just ended it there. We're disappointed with the results, but we're very proud of what we came up with because we know the system works. We know our tires work, our bucket works, our auger works, everything works. And we know if we had a little more time and maybe some other expertise on electronics and that sort of thing, we would have been great.
Kind of nice because it's taking a lot of stress off now. We can just sit back and kind of enjoy all the other teams and just see their designs and actually compete because we've been so busy since we got here. I haven't even seen but half the teams.
We do not get the result that we wanted, but it's still a really good learning experience.
I mean, there are a lot of engineering groups that are just writing papers.
It's been really helpful. It's been really real life.
For next year's team, definitely they need to have 1 or 2 electrical and CS workers.
The more minds from different fields, the better you're going to be.
NASA talked to us last night about like they never can get enough testing done. You can never over-test, and that's definitely the case.
Do a lot of practice just driving the robot around.
Test a lot.
Allocate more time on testing, and things would actually work out really well.
We know that the excavation method itself would have been great. We just really hope that somebody actually takes the auger design and goes forward with it because it worked great for us. Just the fact that things did start to come together made us kind of proud of our design.